next very important concept, that is classification of fluids. In classification of fluids, fluids are classified as follows. They are classified as ideal fluids, real fluids, Newtonian fluids, non-Newtonian fluids, and ideally plastic fluids or ideal plastic fluids. Let us have some discussion on ideal fluids. So what are ideal fluids? Ideal fluids are those fluids which don't have or doesn't have any viscosity, surface tension, and incompressible. So ideal fluids are those fluids which don't have any viscosity, surface tension, and incompressible. This viscosity, surface tension, and incompressible are some of the basic properties of fluids. In nature, the ideal fluids do not exist and they are imaginary. If we plot a graph between shear stress and velocity gradient, shear stress on the y and velocity on x coordinate, the ideal fluids lies on the x coordinate. It is very clear that it is indicated with blue color dotted lines or blue color lines, which means ideal fluids lie on the x coordinate. Real fluids, those fluids which possess viscosity, is called as real fluids. These fluids are also called as practical fluids. So real fluids are also called as practical fluids. Newtonian fluids, those fluids in which shear stress is directly proportional to rate of velocity gradient. In which shear stress is directly proportional to velocity gradient. Here tau is directly proportional to du by dy. So this concept, shear stress is directly proportional to velocity gradient, is very important in our viscosity concept. In viscosity concept, we are going to see shear stress is directly proportional to velocity gradient. This principle is very important for viscosity. So Newtonian fluids are those fluids in which shear stress is directly proportional to rate of velocity gradient. So again, if we plot a graph between shear stress and velocity, we can see it is linear from the origin. Non-Newtonian fluids, those fluids in which shear stress is not proportional to rate of velocity gradient. So mathematically, in non-Newtonian fluids, shear stress is not proportional to velocity gradient. Here tau is nothing but shear stress which is not proportional to du by dy, which means du by dy is nothing but velocity gradient. Again, if you are going to plot a graph between shear stress and velocity gradient, it is not linear from the origin. It is going to take a curve. So this is an example for non-Newtonian fluids. Ideal plastic fluids or ideally plastic fluids, a fluid in which shear stress is more than yield value and where shear stress is again proportional to velocity gradient, which is proportional to velocity gradient. Again, if you are going to plot a graph between shear stress and velocity gradient, it is also linear, but it starts from y coordinate. It is very clear, it starts from y coordinate.